Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could, get this video pushed up the algorithm. Okay, let's do this little Green's theorem problem. Green's theorem, right? This is useful because instead of usually using the single integral, we can turn this into a double integral, and usually that double integral will have an easier region to describe, and we don't have to do any weird things like we usually do for the single integral and trying to find a common variable. Let's start with the picture. Boundaries closed by these two parabolas. Okay, well, I definitely know that y equals x squared looks like this. Okay, what about the other one? Okay, so if you were just to turn your tablet or your screen, and I'm going to literally turn it 90 degrees, like this. And then now I'm going to graph it as if I had a parabola. So I literally I was like this, and I just went like that. That's all I did. And if you don't believe that this works, you could also just do this. X, square root x is equal to y, plus or minus. And that would be that graph. Now, like I said, I think why don't you just conceptually think here and just turn your paper or turn your screen. This is our region inside that we want to integrate, and we want to go about this direction around it positively. Okay, so none of that really matters that much. I just wanted to draw it, but it is useful to actually see the region we're going to want to integrate. Now, Green's theorem is useful because we go from single contour integral, right, to a double integral domain. Oh, don't want to do that. And what is the formula? Let's look up the formula real quick. Yep, and this is the formula right here. So it goes q with respect to x minus p with respect to y. Okay, we'll go back to paper. And dA. Okay, so what is q? What is p? Well, usually our integral is written like this, right? It's a p dx plus q dy. So then we could see that p is equal to y plus e to the square root x. Therefore, dp dx is going to be equal to 1/2. Oh. Okay, I'll do this actually nicely. dx square root x multiplied by e square root x. Okay, so what is the derivative of this? It is 1/2 x to the negative 1/2 e to the square root x, which is all equal to e to the square root x divided by 2 square root. Okay, what is p? Well, oh. Damn, I totally just been wrong. It's py, right? So if we take py, dp, dy, we actually just have a 0 here, and then we just have 1. Okay, see, it was supposed to be a lot easier. Next one, q. What is q? Q is the second one, so q is right here. 2x plus cosine y squared. So then if we take dq dx, right? Well, it's 2. Okay. So then now we have this integral over a domain. We don't know what that domain really is yet. We don't know how to really describe it. But we do know it's qx minus dp dy, which is 2 minus 1, which is just 1 dA. And well, dA, we'll figure that out as we describe D. So we got to describe this region here. Is there a way that we can describe it nicely? Well, we know that it goes from y is equal to square root x, and there's y is equal to x squared. And that goes wherever x is 0 to, we don't know. And we could find that by relating these two. So let's relate these two. X squared is equal to square root x. What is a number that makes this true? X is equal to 1. That is the number that makes this true. Okay, and if you want to do the algebra, you could write it as x squared is equal to minus square root x equals 0. And then, I mean, this is the same thing, but I usually like just to ask myself a question. What is a number that makes this expression, this equation true? And it's x equals 1. So we do know that our domain is equal to, for x, we know it is. For y, we will describe that in a second. It goes from 0 to 1. What about y? Okay, so we have these two functions. Y is equal to these two functions of x. So which one's bigger, which one's smaller? Oh, this is the x squared one, and this is the square root x1. So the square root x1 is on top of this x squared one. That means that this x squared is less than square root x for this, right? If we follow our picture. So it's going to be x squared, y, x square root. Okay, this is our domain. So now we're going to integrate. So all we're going to do is integrate really nothing. We just have 1 here. Our bounds is 1 to 0, square root x squared, dy dx. Okay. And this will become integral from 1 to 0 of square root x minus x squared dx. Pretty simple integral to do because there's nothing here. So you just literally just do the bounds, subtract each other. Oh, great, my screen wasn't loaded. There you go, here it is. Okay, now this is actually an integral we have to do. So be x to the 3/2 divided by 3/2 minus x to the 3 divided by 3. And let's put in 1 to 0 here. So it's going to be 1 over 3 over 2 minus 1/3. And this is the same thing as 2 over 3 minus 1 over 3, which is equal to 1 over 3. So that's our answer. This is our description for this, right? It comes all down to 1/3, but what we did here is we used Green's theorem, and I'm going to write Green's theorem here again. And I'll do Green's theorem in green. Green's theorem. And I'll just write it like this. So we go from p dx plus q dy equals to double integral. And this qx, again, that means derivative of q with respect to x. So qx minus py dA. And of course, there is, obviously restrictions when you can use this Green's theorem, right? But we'll just write one of them. This works for a region that's, yes, doing something. God damn it. That's simple. So, simple, like there's like no craziness going on here, no random holes, no cuts. I'm just gonna write for a region works for a region that's simple. And in this direction, so counterclockwise. Right. Now there is a little bit more actual, nuances to this, but this is a calculus class, right? So they usually give you a problem that you can use it for. Consider subscribing and liking if you found this video interesting or helpful. Leave a comment. Just leave any comment, just so I could get this video pushed up in the algorithm.